Greetings and welcome, friends. Wow, this was amazing. I love it. So today we're talking about a brand new chapter, a brand new zone called combinatorics and probability. Probability you've probably definitely heard of before. Combinatorics maybe you're a little less familiar to you. In case you're wondering, I guess I could throw the little definition of combinatorics up here for you real quick. Combinatorics is the study of different possible arrangements of objects. Combinatorics right there. And a subset of combinatorics is permutations. Salutations, friends. Permutations is the arrangement of objects in a certain order. So I'll throw that there up for you as well, in case you're wondering. So, and permutations and combinations are going to be helpful later on when we end up studying probability in this chapter. We got to know how to count things before I can crawl and then run. No, that's not how it works. So combinatorics and permutations is what we're analyzing today. So permutations. All right, the number of ways objects can be arranged when order matters. Actually, I might even specify that about perms. Permutation, permutations. Yeah, I said, yep. Combinatorics, yep. Oh, arrangement, the double R? That's not supposed to be there, but that's fine. Or the double G. What's? I don't know.
No, the double R.
Oh, wait, okay.
And you put an E in the top of his like arrange and like arrange.
Yeah, you have.
Wow. That's all right. I love this so much. I'm keeping it. It's fine.
Which one's right? I'm really bad.
Nobody knows. No one knows. Actually, maybe this was a play on words of how many ways could I arrange the letters in the word arrangement. No, I guess not. But what's important about arrangement, regardless of how it's spelled, is that order matters when it comes to permutations. All right, so we'll talk about arrangements of objects when order does not matter. That'll be mañana. So let's talk about a situation, perhaps not unlike something I encounter day to day. Let's do our first little example, but it's also simultaneously going to be a bit of a discovery in some regards. Exemple. And you don't necessarily have to write this down in full context. You could just write down 2 pants, 3 shirts, 2 ties.
Oh my gosh,
So, yeah, isn't it great?
No.
So find the number of possible outcomes when randomly choosing between 2 pairs of pants, 3 shirts, and 2 ties. So this would be like, say this is the number of clothing articles that I have for my dress clothes each day, and I go into my closet and I actually don't care whether or not I match in what I'm wearing. I merely just want to be wearing 1 shirt, 1 pair of pants, and 1 tie at the end of it. So I just show up to school however, doesn't care if it matches at all. Right? So this is my situation, and I want to figure out how can I determine the number of possible outcomes. And one of the ways you might have done this is sometimes by drawing a representation of this. I'm going to throw a little sketch in here. This is called a tree diagram right here. And what I do is I have each decision broken up into a branch. So my first decision would be, what pants am I going to wear? Am I going to wear pants 1 or pants 2? Right? So that's my first decision, so I had to branch, right? And then my next decision was, what shirt was I going to wear? Am I going to wear shirt 1, shirt 2, shirt 3 if I'd already chosen to wear pants 1? Or am I going to wear shirt 1, shirt 2, shirt 3 if I'd already chosen to wear pants 2? Right? And then after each of those is a third decision, which tie am I going to wear? So those are branching off, branching off, branching off. And so notice that this endpoint, this node, represents the situation in which I wore pants 1, shirt 2, and tie 1. And this represents when I chose tie 2, shirt 1, and pants 2. Right? So if I just wanted to figure out how many possible combinations were there, I just have to count the total number, which is 12 ways, 12 possible combinations or permutations or arrangements, so to speak, of pants, shirts, and ties. So this would be a very cumbersome way to approach this problem over time. I think you'd agree. The more complicated the problem, you probably didn't even want to draw out this tree. Notice I didn't want to draw out this tree diagram, hence my reason for just merely copying and pasting it from my notes. Dandy. So now one of the reasons that this works is that I was treating these events as though they were independent of one another. All right, independent events have no effect on one another. All right, if I had restrictions, if I said, oh no, I'm only going to wear certain shirts, if I happened to choose the black pants, then those events would no longer be independent. They would be dependent. So independent events are events that do not affect each other. Examples of independent events would be things like, I don't know, flipping 2 coins. Or another example would be like rolling 2 dice. Right? Where the idea is that whatever I get on the first coin has no effect on what I had on the second coin. It's not changing it. They were completely independent. There was no influence.
Throw one dice at the other dice.
And they collide? Yeah, then I see what you're saying, but technically the outcomes are still independent when I'm just recording the data off of those. So even with collisions or whatever, where they actually land, we're still calling that independent, which I think is what, isn't that what, like, what's the elf in Rudolph say? Is that what he says? Hermes, what's his face? Something like, you know what's up. Other types of events are dependent events, when they do have an effect on one another, like drawing 2 cards from the same deck. All right, or if I was choosing only from certain shirts once I chose which pair of pants I was wearing. All right, so that's kind of what's going on there. Right, independent, dependent. I have to actually treat those situations differently as a result, and yeah, it's going to be interesting. So as you're writing that down, I'm going to start telling a story, and I'll draw a picture. You don't have to draw any of the pictures here. So imagine, all right, this is actually a story that my older brother heard from his statistics professor when he was a student at University of Massachusetts Lowell. Does my brother have cats?
No, the one that had to do the snap.
Yeah, same bro. Yeah.
Is it the one that failed the statistics class like 4 times?
No, that was a friend. No, not my brother. So imagine, so this is what the statistics professor said. He said he had a great fear of flying, right? So he was like terrified of flying, not because he was necessarily afraid of heights or whatever, but because he was afraid of a very particular situation in which there would be, of all things, can you guess it? A bomb on the plane. Oh man, this is terrifying. Oh, why? What are you talking about? I'm not teaching people how to make bombs on the internet. Don't worry. The NSA can come find me. I'll teach them math. So he was afraid of a bomb being on the plane. That was his great fear. So yeah, that's the bomb that Batman would be carrying in the 60s version of Batman. So let's say he found out that the probability of a bomb being on the plane was equal to 1 in 10 to the 9th power, something ridiculous, like 1 in a billion planes, all right, has a bomb on it, let's say. It's probably not, well, I don't know, who knows. So let's say that, and he's like, he still isn't brought any comfort from that fact because he's just terrified. I don't know what the phobia actually would be called. It's not fear of flying, it's just fear of bombs on planes, specifically. And he comes up with this solution. He decides to bring, get ready for this. He decides to bring his own bomb on the plane.
Wait, what?
Is this a real story?
This is a real story. I don't know if he actually did it. This is a story that I was handed down to me by my brother from his statistics professor. So his solution was, I'm going to bring my own bomb on the plane.
The statistics professor brought.
I don't know if he actually ever did it. I hope not.
The story that.
Yes.
Okay.
Yeah. It's a story, I assume. So he said, because what's the chance of 2 bombs being on the same plane? Right? It would be 1 in 10 to the 9th multiplied by 1 in 10 to the 9th, which is like 1 in 10 to the 18th, which isn't just like twice as good. It's like crazy, a billion times as unlikely is what it is. I mean, this is 1 over 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros. That's unlikely, right? And so he's like, I'm going to feel so much safer when I can just, put my carry-on luggage in the overhead bin, and I can just sit in my chair, buckle my seatbelt, and just have my bomb right on my lap. Like, I'm going to feel so safe, right? So, and imagine like him getting caught, I imagine he'd never actually be able to board a plane with a bomb on it, or so I hope. Because imagine him getting caught and he's like, no, you don't understand. This isn't a terrorism bomb. This is a safety bomb to reduce the likelihood of other bombs being on the plane that are actually intended for harm. And then he could like sell them on like some sort of television infomercial of like, here, bring your own portable bomb on the plane. Right? Like it would just so reduce the chance of it happening, right? So what's the problem with his logic? Does anyone know?
Bring bombs on planes.
Right, bringing bombs on planes is not a good idea. I agree.
But also, he has no idea
Just because he brings
what
up
number
bombs
plane
doesn't
that
mean
is, and if that's just a statistic. Someone could bring a bomb on a plane any time they want.
Right, but by chance, it's so unlikely. It's like winning the lottery twice in a row. Like, when's that going to happen, right? Same idea. Well, the problem actually is that his event and the terrorist event are not independent of one another. He's actually forcing his event to occur, right? It's his chance of his bomb being on the plane is not 1 in 10 to the 9th. It's 1. It's a certain event. And then the terrorist bomb being on the plane is 1 in 10 to the 9th. All right, so that's just 1 in 10, out of 1 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a W at the end. We'll just turn it into bam, there we go. Right, so that's 1 out of a billion, right? So the fact that he chose to bring his own bomb on the plane was no longer using chance. He was within the experiment forcing that to happen. All right, so those weren't really independent events in that sense. This probability, you know what this probability represents? This would be like if 2 terrorists, right, are on the same plane and one of them stands up and be like, listen up everybody, I'm taking this plane. And then like, but the other guy just across the aisle at the same time was like, we gotta take, and then like they're like making weird eye contact with each other like, I was gonna take the plane. What? Wait, you're taking the plane?
This is our
Who are you?
competition we have
Right.
in America.
Why? It's fine, it's fine.
They're the Malaysian player.
Right? So the idea, like that would be an improbable event, 2 groups of terrorists simultaneously trying to take the same plane. That would be improbable. That would be this event. But our professor, he's out of luck. So don't bring bombs on the plane and trying to ensure your own safety. That's not going to work. So good lesson to learn. So let's talk about independent events, though. And let's talk about what's called the basic counting principle, the BCP. Says, suppose one event, summarize it. It's fine. Or, yeah, it's fine. You're good. So suppose one event can be chosen in P many ways, or P different ways, and another event, independent of the first, can be chosen in Q different ways. Then the 2 events can be chosen successively in P times Q ways. So if they're independent, I can multiply each of the event's possible outcomes to get the successive number of outcomes. So in the case of my pants and my shirts and my ties, all right, back to the first example, I could have just done 3 times, was it 3 shirts? 2 pants, that's right. 2 pants times 3 shirts times 2 ties, and I get 12 ways possible, right, when I end up doing that. So this was the pants. pants, shirts, and ties, right? So it turns out because those events are independent, you can just simply multiply their individual components, so to speak. And you don't have to worry about making huge tree diagrams to represent that situation. Because mathematicians are not interested in doing things inefficiently. They're usually looking for the exact answer, then an efficient way to find the answer, and eventually an elegant way to find the answer. So let's do this example. This is one that you don't have to write down all the details. You could probably just summarize it right here. And so what this says is, well, oh, it's cropped off. Well, I'll fit it over here. It'll be fine. Don't worry, it's fine. P times Q. That's all. P times Q. Well, working at Bartleby's bookstore, you are going to select a set of 4 bestsellers to promote. Maybe they do this on a monthly thing. I don't know, right? And the store is going to promote 1 book from each of 4 categories. So you're selecting 1 from each type of genre, so to speak. There are 4 vampire romance books. There are 4 teenage arena deathmatch books. There are 3 child wizard books, and there are 2 math romantic comedy books. So first question is, are the choices independent? So if I choose one of the vampire romance books, does that have any effect on what I select for the teenage arena deathmatch book? No, so these are independent of one another because I'm only choosing 1 from each category.
Yeah, he really means Twilight, Hunger Games, Harry Potter, and something he made up because that's not real.
What are you talking? Math romantic comedy? That's the best genre of book ever. What are you talking about?
Let's get Emily Jar in here. She works for
I've never wanted to throw myself, but that would be so.
So, question, how many different ways can the books be selected? So for the first vampire romance, how many do I have to pick from? 4, so I'm going to take 4. I'm going to multiply that by the number of teenage arena deathmatch, which is 4, right? Those Hungry Games. Child wizard books, I've got 3 to pick from. I'm only going to take 1, but there's 3 possible choices. And then math romantic comedy, I'll multiply by 2. So let's see, 16 times 3 is 48 times 2 is this, what, 96 combinations or ways that this could occur. All right, so it's not too crazy. Not too crazy. So, so we've talked about, right, combinatorics. We've talked about independent events. I talked about permutations, right? And with permutations, as I said earlier, order matters. Now, in this case, it didn't matter. I wasn't saying like I was going to arrange them on a shelf in a particular order. I wasn't determining that. Order didn't matter for this problem, but order matters in the case of permutations. All right? And so for permutations,
I'm not able to copy this down because
that's
you're going
fine.
so
That's
fast.
fine. Don't worry.
So I'm not taking notes.
Okay.
Like,
Just write down the little example summary.
I'm
Bang.
trying to, but you're going too fast.
So a permutation is the arrangement. Man, that's my awesome spelling of arrangement again. All right, of objects in a certain order. So I tried to come up with some P words to help us with permutation. We already wrote down permutation earlier. It's things such as parades, the order matters, right? Things like phone numbers, the arrangement matters, right? If someone asks for your phone number and you're like, yeah, my phone number's got the digits 7, 2, 1, 4, 9, 8, and 0, right? Like they can't just randomly hit those numbers in any order they want and have it work out. They have to dial it in a particular order. So order matters for permutations. And it turns out we've got a couple formulas to help us calculate these particular situations for permutations. I'm going to paste this right on over this previous one here.
I'm also getting a drink.
So the number of permutations of n objects taken n at a time is defined as n factorial. All right, so this is read as n factorial. We talked a little bit earlier about what factorial meant, where it's just you take whatever integer it is, positive whole number integer, and you multiply it by all of the integers less than it going down to 1, right? So 3 factorial, for instance, means 3 times 2 times 1, right? Or more properly, n factorial would be n times n minus 1 times n minus 2 times n minus 3 times blah, 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 times 3 times 2 times 1, where you just multiply them all out. So if I'm taking all of the objects at a time, so for instance, if I'm arranging seats with 8 students in 8 desks, 8 factorial is the number of possible arrangements of those students. Okay, if I'm just kind of linearly organizing that. All right. We'll talk about permutations with repetitions in a couple days when we specifically analyze things of like, if I'm arranging people in a round table, that kind of messes things up at times. And then the number of permutations of n objects taken r at a time is defined as n factorial over n minus r, all factorial. So I do the difference before I do the factorial there. And that's going to be like if I was taking of my 8 students and selecting, right, figuring out how many can fit in a group of 3 for partner work. So that would be 8 combo or 8 permutation 3 if somehow the order that I selected them mattered. Something to that effect. So let us talk about putting these formulas to use and what this looks like. They're all really short. They're all super short. And actually, yeah, we're just about done. So let's see. It says in a track and field race, there are 3 students competing. How many different arrangements of first, second, and third can be awarded? So there are 3 competitors. I'm arranging them into 3 slots. So this would be permutation 3, 3. Which means I could use the first formula, because, right, those are the same number. And so this is going to equal 3 factorial, or 3 times 2 times 1, or 6 possible arrangements. All right? And order matters, right, if it's first, second, and third. So that's why it would be, right, 6 possible ways. Now, similar situation. Part 2 of this example. What if I had 5 contestants, but still only 3 prizes? All right, so I want to figure out how many ways could those 5 racers be placed into first, second, and third. So this would be permutation 5, 3, right? So n is 5, r is 3, right? I'm selecting 3 from the bigger group of 5. And by the way, n is always going to have to be bigger than r, just so you're aware. So this is going to be the second formula, this one right here. So this is going to be 5 factorial over 5 minus 3 factorial.
So 120.
Yep. I'll actually write this out this way. 5 minus 3 is 2, so that's 2 factorial, or 2 times 1. I just want to get us in the habit of thinking of how these can cancel out. If I was to write these out, the 1s would cancel and the 2s would cancel. So apparently this is the same as 5 times 4 times 3. 5 times 4 is 20, times 3 is 60 possible ways that that could occur. Which, if you think about it this way, this is why this product makes sense. And I agree with you, Jacob, that this would be 120 divided by 2, which is also 60. But this technique of canceling out is going to be helpful later. What if I imagined, okay, I've got first, second, and third. How many racers can I pick for the first slot? Well, there's 5 possibilities, right? 5 possible people.
4 left, and then there's 3 left.
And then there's 4 left for second place, and then there's 3 left for third place. So if I multiplied those, that would also equal 60. So if you kind of broke it down that way and thought about like how many people could get first place, once I've chosen first place, how many were available for second? Because no matter how fast you are, you're not going to get first, second, and third unless, I don't know, unless like all 4 other racers somehow died during the race. I don't think they would give you the medals though. Or if they just like, they all quit. They're like, I'm not racing that guy, and then like you just get all the medals. That'd be pretty great. Let's analyze this one last example. So 10 members on a committee sit in a row at a head table. How many arrangements are possible? So I've got 10 people and 10 chairs, and I'm asking about arrangements. So I'm saying the order matters here. So this is just going to be straight 10 factorial. That's the first formula. And does anyone have any scale on or magnitude as to how big this number is?
I think it's a 10.
It's like 1,000? That would be like 10 cubed. No? Now it turns out your calculator you can't actually do some factorial stuff with. Oh, it's got the blurries. Let's see. Let me grab a blue calculator as well, just to show you. Is it focused yet? Man, yeah, it is not able to focus here at all. Here we go. Let's focus on this first. And then I've got both types of calculators, just so you guys can see that there's ways to calculate factorials. So if I hit, so I want to do 10 factorial, so I'm going to hit 10 on the main screen, Jacob, and then I'm going to hit math, this math button right here. That's pretty funny. That's true. That's true. Yeah, poorly labeled. And if I go over to the PRB menu, probability, I can see some different possibilities. There's actually a simulated random number generator. And that's factorial right there. 10 factorial is that guy right there. 3628800. 3628800. So that's a little over 3.5 million right there. Yeah. So I mean, if you didn't know how to plug that in a calculator, you could literally do 10 times 9 times 8 times 7 times 6, and that would work out as well. And on this calculator, there's a PRB button right here. This one's actually a little easier, so I could do 10 and then hit the PRB button, and you can see, oh, if I scroll over to the exclamation factorial button, I can get the same value that way a little bit quicker. So it is on calculators, factorial button. I wouldn't be surprised if the iPhone calculator probably had it as well. So last part, last example, here we are. If the same committee is now choosing a president, vice president, treasurer, and secretary, how many different possible outcomes can occur? Now, order matters in this case because whoever I chose first, right, is president, so that's different than if I chose them second or third or fourth or not at all. So order does matter, so this is in fact a permutation. I've got 10 people, and I've got 4 positions, it looks like, that they're being chosen for. So this is the same as 10 factorial over 10 minus 4 factorial, which is 10 times 9 times 8 times, and I'm actually going to hold on a second there. 10 minus 4 is 6 factorial, which, watch this awesome canceling move. I'm just going to write that as 6 factorial, and this I'm going to write times 8 times 7 times 6 factorial. Ooh. Because wouldn't you agree that 6 factorial just means 6 times 5 times 4 times 3 times 2 times 1? So that is technically the rest of 10 factorial there. And so if I can choose my kind of like canceling wisely here, I can actually avoid having to write a lot of that out. So I just have to do 10 times 9 is 90, sorry, times 8. What's that? 720 times 7, something like that. And this is 5040. So there's 5,040 ways for that to occur. So, lovely, lovely. Thanks for watching, internet friends. Have a great day. Bye-bye.